All right, so we're going to talk about functional groups today mostly. We'll also get a little into intermolecular forces, but functional groups are essentially things that are added to some kind of carbon skeleton. So if you have like a carbon chain and you have a functional group on it, that functional group has different functions. For example, one functional group might make you drunk or might clean things. Another functional group might be what makes skunks smell, or maybe the additive to certain gases, and we'll talk about those kind of as we get there. But essentially, they change how things react. So let's start by giving an example of how a functional group can change how something will react. So here we have an ethane. Ethane is a carbon to a carbon. It's an alkane, right? It's all single bonded, so it's an ane. And here we have ethanol, where we also have essentially ethane, but we've added this thing we call a hydroxy group, which we'll also come to know as alcohol. So we made it an alcohol by adding this OH to it. Let's talk about how that changes its reactivity. In fact, I'm going to do that with a smaller pen, and hopefully you can see it here. Okay, so it says which reaction occurs when ethanol, which I'm going to draw it in its stick form. I hope you don't mind. So that's ethanol. It's a CH3 to a CH2 to an OH. Is treated with H2SO4. So let's do A first. H2SO4, if you remember from the last lecture, we talked about H2SO4 as an acid. It's going to give off that H, so it's kind of easier to draw it this way with this H here, because that's the acidic H. All right, and we just kind of want to know what's going to happen. So we did practice this a little last time, but essentially, remember, H's want to come off, and that's good. We got a lone pair to take them on. So this lone pair is going to come over here, snatch that sucker up, and then this bond, those extra electrons are going to go to that H over there, this side over here. All right, so what that gives us is, we still have this lone pair right there. But now this lone pair took on an H, and this one also took on an H, and now we know that that's a positive formal charge. Because this one took on the extra electrons, it's an HSO4 negative. All right, so that would be the reaction of this. Let's go ahead and do it with NaH, just to kind of refresh our memories about Lewis acids and bases. So we got plus, so NaH, sodium, we should recognize as a spectator ion. There are really two ways you could do this. You could care about the sodium, or you could not care about the sodium. Personally, because it's a spectator, I like not caring. I like only looking at this as an H negative. So again, this would be something like Na positive and an H negative. But again, this is a spectator ion. It won't be doing anything. This is the important piece right there. So I'm going to react it with just that because it makes it a little bit easier to see. And it's a habit I welcome you guys to get into. All right, now we got to ask, where are the electrons going? Who's donating electrons and who's accepting electrons? And hopefully you recognize that this is a negative, so this is where the arrow is going to be going from, and it's going to be collecting something else. I see this hydrogen right here, going over here, collecting that hydrogen, and then this bond right here will be going back onto the oxygen over here. All right, and what we'll get from there will be an O. Now the O's got these extra electrons there, so it's going to be negatively charged. It's got a -1 formal charge. And this hydrogen, which picked up a nice little hydrogen because it had those spare electrons, is just H2. Okay, so when we had alcohol as a group, we made some new things, right? Depending on which one we were talking, which thing we added. And so that's cool. Let's look at ethane. If we have ethane, which is this one, CH3 to CH3, you could just draw a line, but that looks really weird. And so I'm just going to actually draw out the carbons and not do the skeletal structure. And if we react that with H2SO4, oops, I missed a little H. There we go. If we react this with H2SO4, we know that this wants to give off an H, but where's it going to give it to? Do we have anything that's electron rich over here that's looking to take on an H? The answer is no. Everything's singly bound. Remember, in order for something to grab an H, it has to have extra pair of electrons, or it's got to have some kind of pi bond, which actually we'll go over the vocabulary of pi bond here in a second. So it's got to have a double or a triple bond, or that lone pair. This doesn't have that, so this reaction won't even occur. The same thing if we go in the opposite direction and add something that's electron rich. So if we add this hydride to it and we're like, okay, what is this gonna grab? It's not going to comfortably grab anything without creating a carbocation, which we talked about was a little bit unstable. And so this reaction also won't occur. The point of this exercise is that when we have a functional group on an alkane, such as OH minus this hydroxyl group, what's going to happen is you can get a reaction. So we can change this functional group into many, 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 many different things to get different reactions and different results each time. Okay. So before we can understand functional groups, let's learn some vocabulary. One that I kind of want to go through is, before we get there, is revisiting sigma and pi bonds real quick. So just to refresh your memory, a single bond would be a sigma, a double bond is a sigma plus a pi, and a triple bond is a sigma plus 2 pi's. So just kind of a vocabulary thing. When we talk about a pi bond or something containing a pi bond, what we're saying is that it's a double or a triple bond. It's that simple. Okay, one thing I didn't go over back here is R. So what R means is any carbon thing, any carbon containing thing. This R could be like a crazy skeleton, it could be something, but for example, in this case, this right here would be called R, and it's attached to this functional group here. All right, so I just want you to get used to what R is. So in an alkane, or we just have single bonds, for example, let's say this is the structure. Let's make a little chart here. Let's give you an example, and then what the functional group actually is. Okay, so structure, example, and functional group. All right, so for our alkane, our structure would be like some kind of R containing thing to a hydrogen, just a single bond, some kind of carbon containing thing to a hydrogen. An example would be like carbon to a carbon. So if we're looking at just hydrogen, any hydrogen, this would be the R group. All right, but we have some kind of, it's an alkane, so it's a singly bounded stuff, and the functional group, it would have none, kind of like we just discussed. That's not a functional group. But we can say it is a functional group when we become an alkene. So an alkene would be something like a carbon double bonded to another carbon. And I go like this to represent, these would also be R's, but you don't really know what they are. So I can't call them all R. It looks like they all have the same exact skeleton that goes off of it. Oftentimes you'll see people, I could just as easily call it R and call this one R prime and call this one R double prime and call this one R triple prime. You'll see that as well. But it's just as efficient, I think, to just leave dashes and leave it up to your imagination what they could be. Okay, these are not carbon groups. They're just going to something else. Okay, so anytime you have a carbon-carbon double bond, we call that an alkene. An example of that would be like ethene, like we drew last week. This, its functional group is just that it's a double bond. And again, we should recognize this, we would also call it a pi bond. Even though it's got a sigma and a pi, we'll oftentimes look and say, hey, does this thing have a pi bond? If it's a double bond, the answer is yes. All right, alkyne. By the same token, I'm just gonna leave dashes, empty, unspoken dashes. So we don't know what those things are, but it doesn't matter. We're focused on this carbon triple bond to another carbon. An example would be acetylene here, this are also known as ethyne. This is a triple bond. Hopefully you recognize that. And again, we would say this is a pi bond. Really, it's got 2 pi bonds and a sigma. We know that from up here, but we might oftentimes say it's got a pi bond. Last, let's look at the aromatic. So I'm going to draw a benzene ring. There are several different aromatics. You'll get into that, I think, more in Chem too, because there are different kinds. An example of that would be that. Got it right there. And even though this thing in and of itself is called benzene, we call this a phenyl group. So you'll often hear it referred to as an aromatic ring, or sometimes you'll hear it referred to as a phenyl group. All right, and this is alternating pi bond, sigma bond, pi bond, sigma bond. And these actually resonate throughout. So this pi bond could move there, that pi bond could move there, that pi bond could move there. But generally what I'm looking for is recognize that when you see this sucker, you know that it's unaromatic. All right, some other vocabulary that we need before we can address what's going on here are primary carbons. So you have a carbon, bond it to another carbon, and then some other stuff. Secondary, where you have a carbon, bond it to 2 carbons and other stuff. Tertiary, a carbon bonded to 3 carbons and other stuff. And quaternary, ordinary, it's called quaternary. You don't run into them very often. Okay, so let's see if we can recognize primary, secondary, tertiary, and quaternary carbons in here. So this first one right here, an A, I see that this carbon is bonded to just 1 single carbon right here. Oops, sorry, I realize you can't see that. Okay, so this carbon is bonded to just this 1 single carbon right here. So this would be called primary. This carbon right here, see how it's bonded to this one, and this one, and that one? So I count 1, 2, 3, 4. It's in the center of 4 carbons. That would be a quaternary. Here we have 1 carbon bound to this one and that one. So that's a secondary carbon. Okay, so we got a primary here, quaternary there, and a secondary there. All right, let's look at this one. So it's asking about the hydrogens. So you're looking at the hydrogen, but you look at the carbon it's bound to determine if it's primary, secondary, or tertiary, or quaternary. So for example, this hydrogen is bound to this carbon. So this is the carbon that we're actually looking at. So this carbon is bonded to how many other carbons? I see 1 here and 1 there. So 2 in total. And so this is secondary. Let's look at this hydrogen. It's bound to this one. That's the carbon that we're looking at, this guy right there. And it's bound to 1, 2, 3 different carbons. So I'd call this tertiary. And then this one right here is bound to this carbon. That's only bound to 1 other carbon. So again, we're looking at this carbon. It's only bound to this 1 carbon, and we would call that primary. All right, now that we have some ideas, let's go ahead and get started. So when we have a CZ sigma bond, in other words, a CZ and it's single paired, a Z being something that contains a lone pair, any kind of hetero atom, meaning a different atom from carbon. Anytime we have a different atom from carbon that has a lone pair on it, we're going to, it's going to have its own functional group and its own workings. The reason for that is when you have, it's drawn right there, but it's more fun to redraw it. Do it with my darker pen. We have a carbon bonded to a Z that has some kind of lone pair. What that means is you're going to have a partial positive here and a partial negative here, and that's going to change the reactivity of the atom. So let's talk about each of these examples. So, and by each of them, I mean we're actually not going to go through them very much at all, because you're just going to have to memorize them. By the way, it says right here, memorize. Cool. So you got to memorize them by name. So if I say alcohol halide, you know what it is. So you could also even break this down even further. If that X right there is a fluorine, this is alkyl fluoride. Or if that's a chlorine, this is called an alkyl chloride. Bromine, it's an alkyl bromide. So, so this right here is an alkyl bromide. Okay. Alcohol groups we briefly touched on. Ethers. I'll talk to you more about that in class, but an ether is anytime you have a carbon to an oxygen to another carbon. So it usually ends up kind of in the middle of the chain. We have an amine. An amine is a nitrogen-containing thing. Amines can be primary, secondary, or tertiary, depending on what they're bonded to. All right, thiols. This is the smell of skunk I was talking about. It's generally bad smelling stuff. But you can see it's an SH, so it's not just some Z, it actually is an S to an H, kind of just like the alcohol is also an O to an H. So this whole group right here we would call Z, and this whole group right here we would call Z. All right, and then we have something like sulfide, where you have a carbon bound to an S to this. So very similar to an ether, the sulfides are, except this one has a sulfur and this one has an oxygen. Okay, so now I want to kind of show you how we can classify things as primary, secondary, tertiary based on that. So it says classify each alkyl halide or alcohol as blah, blah, blah. So I see this alcohol functional group right here, right? And the question is it primary, secondary, or tertiary? Well, you don't look at the carbon it's next to. You look at the carbon it's attached to and then ask what that carbon is attached to, if that makes sense. This carbon is attached to just one other thing, and I would call this a primary alcohol. So we'd actually say, and we should get used to being able to say, primary alcohol. Okay? As opposed to this fluorine's attached to this carbon right here, so that's the carbon we're looking at, and it has 1, 2, 3 things around it. So we would call this tertiary, and this would be called a tertiary alkyl fluoride. So whether something's primary, secondary, or tertiary will affect how it reacts. We'll get more into that in chapter, I don't know, 7, I think. We've got some time. But right now we just need to get used to the vocabulary. All right. Okay, so now let's talk about carbonyl groups. Carbonyl groups are anytime you have a carbon double bound to an oxygen. And then it can be whatever else over here. I could put R and R prime or whatever. And these end up being really important. One, because they're stabilized by resonance, right? Remember this lone pair can go up there and leaving this as a single pair, so that becomes negative and that becomes positive, or they can stay there. Either way, this is going to be a partial positive and this is a partial negative, again, because this is a polar bond right there. All right, so all of these have polar bonds. Yes, you have to memorize all of these for the next exam. All right, and there's various different ones. The ones you're going to see the most are ketones. So ketone, I don't know about you, but this kind of looks like a keyhole. It always just reminds me of that. And these, you'll see them a lot, but this one right here ends up being kind of important. Because this hydrogen is acidic, very acidic. In fact, this is like vinegar. You should actually recognize this as a 4.8, right, pKa from the last time we did this. And this has, again, an acidic H. It's in vinegar, acetic acid, ascorbic acid, vitamin C. And so we're gonna need to get used to that one a lot. And of course, you'll see all of these at some point in time. But the important thing to recognize with all of these is that you've got this partial positive carbon in all of them right there at the base of this double bond. So they all have a partial positive carbon, and that's going to be, as we determine eventually, an electrophilic site. We'll actually do it today. Woohoo! Okay, so I want you to kind of go through and find how many of these functional groups you can find in this thing, and functional groups from the previous page. All right, so right away, whoops, I see a carbon double bond there, and you might want to originally circle it and maybe say, even circle this part and say it's an aldehyde, but don't forget it's got this amine right here, this NH2 group right here. And if you look over here, anytime we have a carbon double bonded to an amine group, it's called an amide or an amide, as a lot of people will call it. I'm going to say amide because it's just easier for me, but you can call it an amide or an amide. It just depends on the instructor you get. All right, this, hopefully you recognize that as the aromatic ring. I would not have deducted points if you said phenyl. All right, here, remember when we have an oxygen between two things? This right here is called an ether. Now I see this OH, one of my first things to look at when I see anything with an O is look around and see if there's anything else it's bonded to. It's not, it's to a carbon, to another carbon, and a carbon. So it's just an alcohol. And last but not least, we have this right here, which I would classify as an amine. But you might even take it one step further and recognize that this N is attached to 2 carbons. And remember, we said amines can be primary, secondary, tertiary. This is a secondary amine. All right, we are rocking and rolling, crew. Oh, the fun stuff. This is where organic chemistry really happens. And if I'm being honest, when I first took organic chemistry, I missed this stuff. And nothing ever really made that much sense to me. But it should all make sense if you start from this level and work your way up. So I want to make sure we have a really strong grasp on this. This is the important stuff. Oh, and sorry, my nails are horrible. I painted my nails and then I built a deck yesterday and they just got messed up. Anyways, the deck looks nice though, better than my nails. All right, so functional groups tell us how molecules will react. The most important thing, electron-rich things called nucleophiles. So something that makes something an electron-rich is if it has a pi bond, so right, a double or a triple bond, or it has a lone pair. So if it's got a pi bond or a lone pair, chances are it's going to be a nucleophile. And they react with electron-poor sites called electrophilic sites. The beautiful thing about electrophilic sites is generally if it's a partial positive, it's going to be an electrophilic site, meaning it wants electrons. It's got a positive charge, partial positive charge, and it's looking for electrons. Okay, so let's go through and label these and see how many electrophilic and nucleophilic sites we can find. Again, nucleophilic are pi and lone pairs, and electrophilic are those positive things. So I'm going to zoom in a lot here. Okay, so on this bromine, even though there's no electrons, it's kind of weird to get used to. There's no electrons drawn. We should recognize that that is an electronegative thing, meaning that here we have a polar bond between the carbon here and the bromine there. This is partial negative. This is partial positive. Because of that, this partial positive, remember, partial positives are going to be electrophilic sites. And anytime we have a lone pair, this bromine is going to be a nucleophilic site. So the lone pair made this nucleophilic, the partial positive here made that electrophilic. Let's look at the next one. Okay, I see this pi bond right here, that site right there, that's going to be, because it's a pi bond, it's going to be nucleophilic. Also this sulfur, we should recognize it has 2 double bonds on it. That also makes it nucleophilic. Now let's talk about electrophilic sites. This sulfur, keep in mind, is more electronegative than carbon. So it's pulling electrons away from carbon that way and that way. And what that does is it leaves this carbon partial positive and this carbon partial positive. And again, anytime we have a partial positive, we're going to say that that's electrophilic. So we're saying these 2 sites, there and there, are electrophilic sites. All right. Now we're moving on to this one. So kind of the same token, we'll start with this oxygen down here, which should have the lone pair right there. 2 lone pairs, 1 there, 1 there. So anything with a lone pair, again, it's gonna be hard to label all of these, but maybe I'll try my best. I'll just use E and N if that's okay with you. So here we have lone pairs, we know that's gonna be nucleophilic. Okay, here we have a partial positive and a partial positive because the electrons are getting drawn toward the oxygen. So these would be an electrophilic site. Nitrogen is here. Nitrogen has a lone pair. That makes it nucleophilic. It's drawing electrons, though, this way, away from this carbon here, which would make it electrophilic. Over here, oh, we should really recognize this one, because remember, the carbon to double bond to oxygen, that makes it really reactive. This right there is definitely an electrophilic site. And the double bond here is nucleophilic, and this lone pair is also nucleophilic. So a couple nucleophilic sites on there. All right, so these are all potential reaction sites in this organic molecule. And understanding that is really going to help you. All right, let's see if we can even practice some of these. So a nucleophile, what happens is because the nucleophile has the extra electrons, the arrow is always going to move from that and then grab the electrophile and pull it towards it. All right, same thing. You have a nucleophile here with the extra electrons, and it's again going toward the a nucleophile with an extra electron going toward the electrophilic site. So notice they're always moving. The end of the arrow is always starting with the nucleophile going to the electrophile. All right, so let's see if we can consider if these reactions would happen. Okay, so just to remind you one more time, so we have it on this page, because I know this is new and there's a lot of terminology. When we're talking about a nucleophile, we're saying something with a lone pair or a pi bond. In other words, a double bond or a triple bond. When we're talking about electrophile, we're talking about something that has a partial positive or even a full-on positive. All right, so let's get to work. Bromine is more electronegative than carbon, so it's going to be polar. It's going to have a thing like that. So this bromine has extra electrons. That makes this end nucleophile, and this end right here is electrophile because it's partial positive. Oops, I just drew sigma. Partial positive. It's delta. It's reacting with this oxygen. I hope you can see this oxygen and immediately say, yeah, that's a good nucleophile, because not only does it have extra electrons, it has even a full-on negative charge, meaning these electrons are looking for somewhere to go or something to grab. So this is definitely a nucleophile. So the question is, will these react? Well, if you have a nucleophile and any electrophile, so there's got to be a nucleophile and an electrophile, or a nucleophile and an electrophile over here. So they have to be opposite. As long as you have 2 opposite sites, they can react. So the answer is yes. Why? Because we have a nucleophile here and we have an electrophilic site right here on this carbon, which is again partial positive. Draw it a little better. I'll zoom in too. All right, let's look at this guy. Okay, here I see we have some triple bond. Remember, triple bond represents a nucleophile, so we got a nucleophile right there. And here we've got all these extra electrons. It's a good nucleophile right there. It's got an overall negative charge. But you have a nucleophile and a nucleophile. Will that react? The answer is no. You need an electro and a nucleophile. All right, what about this one? I see a carbon to a double bond oxygen. I immediately know this is a good electrophile. It's got that partial negative or partial positive charge right there. I got the pi bond here, the negative here. This is nucleophile, and this chlorine looks like that. This would also be a nucleophile. All right, then we have this guy right here. I see a negative charge. I see lots of extra electrons. This is absolutely positively a nucleophile. So this nucleophile could attack right here and this electrophilic site right here. And this is a yes. Just the only question is, do you have a nucleophile on one side and an electrophile on the other? All right, here we have a triple bond. We recognize this as a nucleophile. This is something you don't see a lot, right? A bromine cation, where you have a positively charged thing and only 6 electrons. Remember, bromine negative would have 8. And so this actually is an electrophile. Again, anytime we have something positive or even full-on positive, it's going to be an electrophile. And so this would actually react. It'd be a fast reaction, actually. It'd happen really well. All right. Some other things that we didn't go over, which have nothing to do with what we just did, really, are intermolecular forces. I just kind of want to remind you of what intermolecular forces are. Van der Waals, these are the brief temporary forces. So like, let's say you have something like this, I don't know, which is like a butane. There's nothing polar on this. It's just carbons and hydrogens. We remember carbons and hydrogens are non-polar. So there's nothing really moving, but the electrons are still moving back and forth inside the molecule. So maybe at one point, briefly, it might happen that maybe there's like a slight partial positive and a slight partial negative over here. And it might happen to align up at the exact same time that this one maybe has a partial negative and this one has a partial positive, and these things would be attracted. Remember, when we're talking about intermolecular forces, we're talking about forces between molecules. So you might have a brief interaction. So all molecules have these. All molecules have van der Waals forces. Then we have dipole-dipole. Dipole-dipole has to do with polarity. So for example, if we have let's draw this ketone here, used to vocabulary. So if you have a ketone, I have got my partial negative here, or partial positive here, my partial negative, I can't write as fast as I'm talking. Oxygen would be the partial negative, here's the partial positive. And what would happen is if you had another molecule, it could line up this way, where we have a partial positive right here and partial negative right here, and these two molecules could be attracted to each other that way. And this is called dipole-dipole. You know that though, but it's between polar molecules. That's just what I really should write. So anytime you have a polar molecule, you're gonna have dipole-dipole forces. Hydrogen bonding is more specific. Hydrogen bonding is stronger. By the way, strength goes like this, where hydrogen bond is gonna be the strongest for now. And hydrogen bonding is anytime you have an O to an H, an F to an H, or an N to an H. So anytime you have one of those situations, you're going to have hydrogen bonding. Hydrogen bonding again, it acts a lot like polar, like dipole-dipole bonding, but it's not, it's stronger. So let me give you an example. So let's say we have some alcohol here. Let's make this an O to an H. These all look like little people. Okay, so if you have an O to an H here, this is going to be a strong partial negative, and this is a stronger partial positive. The reason for that, the reason hydrogen bonding is stronger, is because this hydrogen doesn't want electrons at all. So oxygen holds the density of the electrons, the majority of that electron density. It's keeping it towards it. So it's close to being almost a full-on negative and a full-on positive. It's pretty close. And so if I take another thing like that, in fact, I'm going to redraw this better. Let's go over here. Foop, foop. O to an H. Again, we have a big partial negative and a big partial positive over here. And we have another molecule that comes in. It could do the same thing. H to an O, like this. So the same molecule, where this would be a strong partial negative and this would be a strong partial positive. These guys interact and these guys interact, and it keeps them together even tighter. All right, I have several videos going over intermolecular forces. I'm not spending a ton of time on it here because, again, it was covered in Gen Chem 1, it was covered in Gen Chem 2. But we will talk about how that affects boiling, melting point, etc. Just not in as much detail as I normally would go over it. So I'm sure you can find a supplemental video of mine on intermolecular forces. Okay, so it says rank the following compounds in order of strength and increasing molecular forces. So let's draw each of these out and we'll rank them. So we've got, this is pentane. This, we have butane 1 all. What that means is you got 1, 2, 3, 4 carbons, and on the first carbon, you have an OH. So I'm just gonna put it there. I'm gonna call this one the first carbon. You could have put it over here, called that the first carbon, it would have been the same thing. A butanal. So 2, 3, and then this one would be an H, and this is double bonded to an oxygen. So essentially that's what that is. And we shouldn't know that naming quite yet. Naming doesn't come up until later chapters, although we have talked about simple ones like this. Okay, so let's go through and label forces. The first is, do any of these have van der Waals forces? And the answer should be yes. Van der Waals, I'm just going to put van Waals. They all have them. Why? Because they are molecules. So any molecule has van der Waals forces. Remember, those are the brief, temporary, moving forces that quickly, that kind of quickly move throughout the molecule, and once in a while, two molecules align, they have a brief magnetic interaction, and then that's it. All right, so they all have van der Waals. Then let's look at polar. So are any of these dipole? Again, polar means dipole. So this one's no, it's not polar. It, as far as I can tell, it only has van der Waals. This one has an oxygen to a hydrogen. What that means is that electrons are going this way. This sucker's polar, and this is dipole. This one also has electrons moving up that way. This is also dipole. Awesome. Okay, now let's look at the last one, which is hydrogen bonding. So remember, hydrogen bonding is only the fun stuff. I didn't really introduce it that way, but the H to an F, H to an O, or H to an N, if you don't have that direct bond, then it won't have hydrogen. But I see right here we got an H to an O, and this has hydrogen. Okay, so this one would be the strongest. It asks us to rank them in order of increasing strength. Okay, so that would be, this one's number 1, it's the weakest. This is number 2, and this is number 3, the strongest. Again, hydrogen bonding trumps all. All right, it says increased molecular forces mean increased boiling point, increased melting point, and decreased volatility. Volatility is how easily something evaporates. So if it's got these molecules that are holding together really tightly, they don't evaporate very well. So you'll have low volatility if you have a lot of forces. In other words, this right here, this butanol, it's gonna hold on to each other better. So this one will have a much higher boiling point than, say, this one. This will be way more volatile, meaning it will want to evaporate very quickly. So anyways, that's volatile, and this has a higher boiling point. All right. Okay, so which pair has a higher boiling point between these two? I noticed right away this one's polar. So this is dipole. This one does not. So this one's going to have the higher boiling point. We look at these two. They look very similar. They have the same masses. But this one right here, I see it has an O to an H. So it says hydrogen bonding. This one does not. So this one would have the higher boiling point. Some other things to think about that help us when we're talking about functional groups, as well as interactions. Things with similar intermolecular forces and even similar functional groups like alcohol and an alcohol are going to be soluble in each other. In other words, polar compounds like polar solids will dissolve in polar solvents. Remember the difference between a solute is the thing that dissolves, So like, I'll give you an example once I write this. And a solvent does the dissolving. So for example, sugar, water, sugar would be the solute and water would be the solvent. You're going to never even forget that because you'll use the term solvent so much that you'll just get used to it. Okay, so solvent is usually like the liquid thing, and the solute is usually going to be like a solid. Okay, let's talk about how that works. Okay, so I'm recording this whole second part of the thing again because, or this last page again, because I want to include a joke. Totally pointless, but okay, we're including it. All right, so let's look at, here we have butane. So we've got this 4-carbon thing. It's not polar, right? It's only got van der Waals forces. But it is kind of important to note its structure too, like its functional group structure. So these are all, it's an alkane. So it's alkane, it's nonpolar. All right. And then over here, we'll be looking at acetone, which hopefully you recognize as a ketone now. This also has a little bit of alkane, right? Carbon, carbon, carbon. But it is also polar. All right, now let's look at these two solvents. We have CCl4, carbon tetrachloride. Okay, and carbon tetrachloride, it's alkane, it's carbon singly bonded to things, and it's nonpolar. Because you have these chlorines pulling in equal and opposite directions, so the overall thing is nonpolar. All right, and then we have water, which is no alkane. So it has it's not organic. It's not organic at all. There's no carbon to carbon single bond or carbon to something single bond. So no alkanes. But it is polar. Okay. So let's go through each of these. Let's look at butane. So butane again, right here, is an alkane and it's nonpolar. So it won't dissolve in water because water doesn't have any alkanes and it's polar. So therefore it's going to be insoluble. All right, insoluble. Again, that's because nonpolar and it's an alkane. But going through this one, again, butane's an alkane. Carbon tetrachloride is also an alkane and it's nonpolar. So let's go back up here. Butane, alkane, nonpolar. That happens to be the exact same thing as carbon tetrachloride, alkane, and nonpolar. So these are like totally similar. And this sucker is going to be really soluble in CCl4. All right, now we look at acetone. So acetone, this ketone right here, it's an alkane. It's got this carbon to a carbon to a carbon group here. And it's also polar. So it works really well because you can, it can dissolve in water. This is actually technically a liquid. So it will be miscible in water because water is also polar. And it'll be miscible in this because this is an alkane. All right, so pretty cool. And because I didn't do a very good job explaining miscible, let me do this. Soluble is when you have a solid going into like a liquid and they dissolve. Miscible is when you have a liquid mixing with another liquid and they mix well. So like water plus oil, kind of the standard example, is not miscible. It's like dropping a rock in water. They don't dissolve each other. And it's because of this. So, all right. Anyways, So that was the whole point behind that, was so I could show you this joke, which is, so this guy's like, but bears are insoluble. And then this guy's like, easy for you to say, you're not polar. Anyways, yeah, pretty great. Okay, so moving on. Let's look at this. It also depends when we talk about things that are polar or things that have similar functional groups, being able to dissolve other things with similar functional groups. So here we have an OH group, and that will generally dissolve in water. But if that OH group has a ton of these alkenes or alkynes, this organic matter over here, then it's not going to be soluble. In fact, there's a specific amount for every OH group. If there's like 5 carbons between OH groups, it's going to be insoluble. And I have it written down here for you, just in case. So ethanol will dissolve in water. You know that if you've ever put vodka in water or something like that and mixed, it's miscible. But however, if you take cholesterol and mix it with water, it doesn't work. Even though it has this OH group, there's still all these alkanes that are keeping it from dissolving. So there would actually be, this actually looks, reacts a lot like a fat. It'll just sit there on top. Yeah. And that's kind of what a lot of people think in terms of building up plaque, but there's been a lot of research to the contrary, but I'll save that for a nutrition class. Okay, so which compounds are water soluble? So let's look at these and have an idea of what's water soluble, because that ends up being really important. Again, things that are water soluble are going to have like functional groups. Functional groups to water. So is there an OH on it? Is it polar? And another thought is also ionic compounds. The reason for ionic compounds is you have a positive end and a negative end, and nothing's more polar than that. And so ionic compounds will also dissolve in water. So let's look at these individual things. So A, we have this sucker, and I gave you the solutions, but again, that's just because I think this is kind of important stuff to know. So we have this long chain of carbons. So I recognize right away, that's a lot of carbons. It's more than 5. So those 5, if you have more than 5 carbons, they'll offset the polar nature or even the OH nature of a functional group over here. All right, so even though we have something polar here and something polar there, it doesn't matter because this is not enough, and because of all these carbons over here, so this would be insoluble. A is insoluble. When we look at B though, we got an OH there, 1, 2, 3 carbons later, we got another OH, 1, 2, 3 carbons later, we got like all these OHs everywhere, tons of polar stuff going on. This is definitely soluble. So insoluble, very soluble. Let's move on to this one. So at first glance, we have a whole bunch of carbons. We have hydrogen bonding with the N to the H, right? So those are generally soluble. But if you look, you might be like, I don't know, there's a lot of carbons over here, kind of taking away from the NH, and it's more than 5 as far as I can count. But there's an important thing about this sucker, and that is I see a negative over here and a positive over there. When you have a full-on negative or a full-on positive, that makes this thing ionic. And that makes it very, very, essentially more than polar. And so because it's ionic, this is going to be soluble as well. All right, if you want some more explanation, I like this one because I didn't write down the carbon rules, which was mainly just this thing. So if you have a functional group with an N or O that can hydrogen bond in water, you need to have it every 5 carbons or else it won't matter. All right, I hope that helped, and I'll see y'all later.